Hello and welcome to this video. This video is for one of my Patreons, a gentleman called Fraser. But when he asked the question, I thought, you know what, that's such a good idea for a video. And it's all about these things, servos. Now, particularly if you're coming from quadcopter land into fixed wing, and check out all of my videos, introduction to fixed wing and some other ones as well. I'll put links down below. Then you might be coming into that part of the hobby and coming across these things. Now, most of the ready to fly models have these inside already, but for those of you that like to build, then it's great to get hold of a cheap wing kit, put your servos and other things in as well, and get it all flying. Now, there's not a lot of information aimed at newer pilots who are coming into the world of fixed wing about servos and some of the things that you need to know. And Fraser was asking some great questions. Things like, what's the difference between analog and digital? How much should you spend for a quality servo? What is a good and bad servo? What makes the difference? So I've put this video together aimed at all of you who want to know those kind of things. So if you know about servos and you've been flying for a long time, this is probably not the video for you. But if you're sat there wondering what the difference between the update speed in things like iNav is for servos, then this is going to answer those questions. So let me dive into the slides and run through some of the topics. But the first thing we're going to do is show you exactly what is inside a servo like this to explain how all the little parts work. So if you've ever taken a servo apart, this will look kind of familiar, and crammed inside that little case is what appears to be a lot of watch components. Now, if we go round this diagram, I'll kind of explain how each of the pieces move and what they are. We'll start at the very top with the white piece. That's the output shaft, and that's the piece that you put the different arm onto, and that rotates either clockwise or anti-clockwise in relation to the signal that the servo is getting. So that's the bit that produces the mechanical movement. Now, that is actually driven by the purple bit. Now, that's a gear train, and the job of the gears is to reduce the very fast low torque movement of that motor into a much slower higher torque output for the shaft itself. And there's lots of little gears in there that do that, and typically those are made of a nylon or another tough plastic, but more expensive ones use some form of metal. The electronic parts are at the bottom. If we look at the orange square on the left, that is the potentiometer. Now, as the output shaft moves, it's moving a little contact on a variable resistor, and that change in resistance is being measured by the control board at the bottom and used to detect the position of the output shaft. The green board at the bottom is the brains, and its job is to move the output shaft to match the PWM or the signal that it's getting. And how it does that, it uses the motor to move the shaft, and it's listening to the value of the potentiometer to make sure that both of them match. And when the potentiometer value is right for the signal that it's getting, it stops trying to move the motor. However, if you try to move the output shaft by hand, then it will increase the power to the motor in an attempt to stop it moving away from the position that it's been told to keep it at. So what makes a better servo? Well, the output shaft might not be made of plastic, it might be made of a metal, and that will make it a lot more durable. The gear train also can be made of other things apart from tough nylon, and those are typically going to be some kind of metal alloys. But the big things that can make a difference is the quality of things like the potentiometer. The potentiometer is a variable resistor. Now, those of you that might have had old style audio equipment where the volume control is a variable resistor, you'll know that over time those tracks can get dirty, and as you play with the volume control, you get lots of clicking and popping noises, and you can use things like electrical contact cleaner to clean that out. And this is exactly the same. And a lot of these potentiometers on the very cheap servos are not great quality at all, and it's a physical contact moving along a very thin conductor, and that over time will wear out. The other thing at the bottom then is the motor. Higher quality motors with more torque, better speed will give a faster and more positive reaction. And then you've got the digital control board at the bottom. Most of the cheap and cheerful servos that you're going to come across are called analog, and they run at a lower update frequency, and they're not as quick or precise. They typically use less power as well, but more expensive servos tend to be digital. Digital servos are a lot faster, produce a lot more torque, but usually use a little bit of power. But I'll talk about that in the next few slides. So choosing a servo, things to think about. Well, they do come in lots and shapes and sizes. The 9-gram size is pretty standard for smaller general fixed wing models, and they're the most common that you're going to come across, typically with a plastic output shaft and plastic gears. But watch out for that output shaft. Not all of the servos out there have exactly the same splines for the thing to fit on the top of. So you can get into a situation where you might have one servo, buy another one from somewhere, manage to fit it into your craft and find that the output shaft doesn't fit. So be careful of that. It's not a problem, you just use the new servo horn that comes in the pack, but just makes sure the spacing is the same, the distance from the actual shaft itself to where the control rod is connecting, so you get the same throw. But be careful with servo sizes, even 9-gram ones, as more expensive servos that are using better quality components or different components can be different physical sizes. Check in the listings and measure the one that you have to make sure that you're going to get the same size, particularly if it's not a little foam model where an extra millimetre or millimetre and a half isn't going to be a problem. Always check the reviews of the servos that you plan to buy. Places like eBay, I occasionally will buy a bag of cheap and cheerful servos, and out of the 10 that I buy, I will probably expect at least 2, maybe 3 to be dead on arrival. But I will use the spares out of them. I'll clip the leads off for other things, for things like S-bus connections, and I'll reuse the servo horns and keep them in the spares bin for other things. And that is because the cheaper servos are a bit of a lottery. If it's got a brand name on it, and the brand name, things like Turnigy or High-Tech or something like that, there's a chance that there's been a little bit more effort put into the quality assurance before it got shipped out of the factory. The stuff that you're buying in places like eBay probably has never ever been tested, and it's one of the reasons that you probably get quite a lot of DOA kit. Going back to my point before, don't forget digital servos will usually be faster but need more power and support a higher update speed too. If you're running something like iNav and you're setting the servo update speed, 50 Hz is what you'd set an analog servo to. Something like 150 Hz might be something that you set a digital servo to. If you're in doubt, set it to 50 Hz. A digital servo won't run optimally at that update speed, but if you try and run an analog servo at the faster update speed, i.e. more than 50 Hz, it'll probably get quite upset. Also be aware that most servos will run on 5 volts, but you can get high voltage servos as well that run in 6, 7 and even higher voltages. Most of the stuff that you're going to come across in the hobby is going to run at 5 volts, so that is what I would stick with, certainly initially. When you're looking at servos, I wouldn't get too worried about this in the early days. I tend to use cheap and cheerful 9-gram plastic geared servos for pretty much anything. And in fact, if you look at the Ready for 5 models on the channel, you'll find the majority of them come with that stuff as standard. And the things you're really interested in is the speed, how quickly it moves. Torque is how much turning force is produced. Voltage is exactly what you'd expect, the voltage it's going to run on, the physical size of the servo itself, the gear and output shaft material, plastic in majority of cases, unless you're doing something particularly robust, is probably going to be fine. And as I said, a brand name is probably going to be better. Doing something from eBay with clone or copy servos is a lottery, and you need to treat it as such. So what would I look for in those things like speed and torque? So for me, if I'm looking at a regular everyday 9-gram servo, I'm going to look for a servo around 0.1 seconds for 60 degrees is good. 0.12 seconds for a 60 degree movement is pretty normal. Most of the time, we're not going to need faster than that unless you are building a very high performance wing. Torque, I'd like to see something about 1.8 kilogram in the specs. 1.6 kilograms per centimeter is entirely normal. The specs, I would normally make sure that's going to run at 5 or just above 5 volts. Size, obviously get one that's going to fit the application that you have. And the gear and output shaft material, metal is going to be best usually. Plastic ones are going to strip in the event of a crash, but they're so cheap and cheerful and easy to replace, then it's usually no great shakes. Just be careful also to make sure that you're getting a servo with the cable that's long enough to actually reach back into your receiver or your flight controller. Other things that you might want to look at: operating angle, how far the output shaft rotates. That's reasonably standard, but always worth a check to make sure that you're not getting an exotic servo that's going to behave differently. Particularly useful if you're going to use them in something like an aileron, where you're going to have one in each wing. And by using that list, I can usually very quickly check that the servo I'm looking at is going to do the job for 90% of the building that I'm going to do here. So whenever I get a servo, I wouldn't rely on it straight out of the package. Because servos are so cheap, they aren't tested. So I would get yourself a servo checker and plug it into the servo checker and move the servo backwards and forwards a few hundred times to make sure that that potentiometer is going to hold up. Servos, if they're going to fail, in my experience, will usually fail in the first 40 or 50 movements. And then once they get past that point, they're probably going to be fine. Also check the centering. Keep going back to the 1500 value, which is the center value for the channel, and make sure that the servo is going back to exactly that same point. Run it some more and use the servo exercising function on the servo checker to put another 100, 200 movements on it, and then make sure it's recentering again. If it doesn't recenter reliably, just clip the lead off, save all the extra bits and put it in the bin. Don't use it. And the last check I do is just to make sure that the gear train and pot health are all fine, that there aren't any gears or teeth that have been rounded off. Try and move the output shaft with it all powered up. Just gently push on it and you should find it very, very hard to move. In fact, it shouldn't move at all. It'll start buzzing as the motor puts more and more power out to try and maintain the position, and that's what you want to happen. Again, if you can move it or you can slide the output shaft around without it really fighting you, then put it in the bin. Another common question that I get is how much power do I need for a servo? Now, I'm not going to go through this in too much depth. The current testing can be done on the bench and you can put some weight on it and try and move it and see how much weight it's going to pull. But I would use these as a rule of thumb. I would say that the normal running current for a servo is going to be around 100 milliamps, but the stall current, i.e. when the servo is unable to move but trying to move, like it was when you're pushing against it with your finger, can reach as high as 700 milliamps, even a little bit higher. So check the specs, as the max current can be very different depending on the servo, but I use a rule of thumb that for normal operation, 250 to 300 milliamps for each servo is going to be fine, with a 1 amp headroom in case of one of those servos getting caught up and binding and pulling a lot of current. So with those basics in mind, let me talk a little bit more about how much power do you need. So let me look at some popular models to get an idea of the BEC ratings, because the battery eliminator circuit that's inside of the ESC is providing the 5 volts that the receiver needs, but also is powering the servos too. If you look at something like the ZOHD Dart, that has 2 4.3 gram micro servos, really small little servos with a 5 volt 1 amp BEC, and that seems to work fine. The Dart XL, a much bigger model, has 2 metal gear servos, again still 9 gram, but this time it has a 5 volt 3 amp BEC. But that 3 amp BEC is more about making sure there's power there for flight controllers and other things as well. Looking at something like the Hobby King Bixler V2, that has up to 6 9 gram servos, but has a 3 amp BEC. So that's probably about the maximum that I'd want to run on 3 amps. Looking at the Avios Grand Tundra, a great big plane, a really beautiful plane to fly and a lot of fun actually, has 6 servos with a 5 volt 5 amp BEC, and that makes sure that even under heavy load those servos should perform fine. And looking at the last one, the Avios Spitfire has 2 9 gram servos and 4 17 gram servos. They're quite beefy ones out there in the wings, and that has a 5.5 volt 5 amps BEC. But that is actually a switching BEC, which is a little bit more efficient and a little bit fancier. So hopefully by looking at that list, you can see that the rule of thumb is a 1 amp BEC is fine for mini wings that use a couple of micro, i.e. sub 9 gram servos. A 2 amp BEC is going to be fine for 2 9 gram digital or 3 to 4 analog servos. A 3 amp BEC is going to be fine for up to 3 digital 9 gram servos or about 6 9 gram analog servos. And 4+ more amps is great when you want to use larger servos with much more power and torque for bigger models and when you want peace of mind. If in doubt, always put in a larger battery eliminator circuit amp rating than you think you'll need. It's not a problem having a BEC that's going to produce 5 amps and only having 2 5 gram servos in. It'll mean that even if both of those servos stall, it's not going to pull down the 5 volt line and potentially cause your receiver to reboot. So now we've talked about that, last couple of things to think about. I am happy to order servos from eBay, and I don't mind that there's a few in the batch, but you have to be prepared to go through and test all of them, as nobody else probably has before you get them. You get what you pay for with servos, but decent analog plastic or metal gill servos will do for most part flyers and wings easily. I wouldn't get too worried, particularly when you're starting out, about the particular speeds and ratings. You're going to do an awful lot of crashing, and you're going to be stripping an awful lot of servos. I've even managed to strip metal gear servos today, and I tend to go for plastic servos just because I have loads of them in the spares bin, and it's a relatively quick job to change them out. Personally, I don't use a lot of digital servos as well. I don't find the benefit. I don't fly aggressively or doing really fast maneuvers where I need that extra speed. So if you're coming into the hobby from multi-rotors into fixed wing, I'd stick with analog plastic geared servos. Unless you fancy spending a little bit more money, then I would probably go for metal gear servos. If you're not sure about a servo when you are testing it on the bench, swap it, put it in the bin. This is also why I test the servos in planes before I wire everything up. So if you watch my building series, it's part of my build process to move the servos with the servo checker, just to make sure that I haven't accidentally managed to get a servo inside my plane that's going to crash it within 2 seconds of me trying to fly the thing. And if you do crash, do make sure that the servos are okay, and do check out the servo that was attached to whatever control surface got banged in a crash. It might look fine on the bench, but you might find that if you try and move the control surface by hand with everything powered, that just like the servos we talked about before, the gears will have slipped and teeth or something might have been damaged inside the servo. That means it's no longer fit for purpose and needs to be replaced. So with those things in mind, hopefully that helps explain a little bit about servos and how they work. You can spend hours looking at servo charts, and people can get very passionate about different servo types. As you get more advanced in the hobby, you might want to spend more on your servos and have faster servos with higher torque, more exotic materials that are harder wearing being used for the shaft and the gear train. But with all of the planes and wings that I get through here to look at, review, and the ones that I personally fly, I'm not particularly worried if it turns up and it's using good old-fashioned black or blue coloured 9-gram servos with plastic gears. Thanks for watching the video and watching right to the very end. You can find me in all the usual places on social media, and if you like the video and like what I'm doing here, then hit the subscribe button and hit the bell notification icon too. If you really like what I'm doing, you can go the extra mile and become one of my Patreons for access to me directly for support, and also giveaways and regular updates too. If you're looking for particular content, then check out the playlist. I organise all of my videos into playlists, so if you're looking for a particular topic, you can find everything here. If it's called Introduction To, it's designed to start very simply and build on that simple introduction to teach you all about it. If it's called For Beginners, then that is really aimed at people who are brand new to that part of the hobby. You can also search on YouTube for anything that you're interested in using the search function at the top. So iNav Painless 360 will find all of my videos and even the playlists around iNav. So thanks again for watching, and happy flying.